These are the practice problems for lesson 12, using graphs to compare relationships. And in problem number 1, you are given 6 graphs, and you are also given 6 equations and asked to match each equation with each graph. And before we get there, what I wanted to do is make a drawing of each one of these graphs. I'm going to also write the equation for each of these graphs. So in essence, I'm answering the question, but I want to do it all together because I wanted you to see the comparisons of these. And as you compare these graphs, they're all proportional relationships. They're all straight lines that go through the origin, 0, 0, but they have different constants of proportionality. They have different slants, different steepnesses. And I want you to compare that slant to when y is equal to x. So this is a constant proportionality of 1. Y equals x. Y divided by x equals 1. So when you're at x equals 1, y equals 1. X equals 2, y equals 2. X equals 3, y equals 3, and so on up to 4 and 5. And I'm going to use these squares as a way to look at the drawings of each of these graphs. And I'm going to talk about salary or money that you're making per hour. So that would be an hourly wage, how much you're making in each hour, or how much you're making compared to how many hours you work. So in the first case, you have 1 square shaded in out of 4. So this is like working 4 hours. And how much money do you get paid for working that 4 hours? Well, you get paid $1. So it's $1 for every 4 hours that you work. So the relationship is 1/4 the amount of money for the number of hours you work. So that works out to being 25 cents per hour when we get to that point. So it's $1 for every 4 hours of work. X equals 4, y equals 1. And that makes the constant proportionality y, or 1 divided by 4, or 1/4. For graph 2, this is showing the relationship of working 3 hours. So x is 3, and getting paid for 2 of those hours. So you get $2, not 2 of those hours, but you get paid $2 for working 3 hours. So that relationship is for every 3 hours of work, you get paid $2. So it's y divided by x, or 2 divided by 3. So for every 3 hours of work, you end up getting paid $2. So that's y equals 2/3 x. 3 hours of work, you get paid $2. So that's right here. So there's the 3 hours of work, and this is getting paid $2 right here. For graph number 1, you're working 5 hours. So x equals 5. So you work 5 hours. How much do you get paid for that 5 hours of work? You get paid $4. So this is y equals 4, $4 of pay for 5 hours of work. So $4 of pay for every 5 hours of work. So that constant proportionality is 4/5. Y equals 4/5 x. So what that's saying is y is always going to be 4/5 of the value of x, and that 4/5 is going to be the amount of money that you earn. So y, this 4 right here, is always going to be 4/5 of whatever x is. Now this is interesting in that now you get paid more money compared to the number of hours you work. So now you work 3 hours, x equals 3, but you get paid $4 for working that 3 hours. So the relationship is now you're getting paid more dollars than the number of hours you work. So it's 4/3 the number of hours. So it's $4 for working 3 hours. So the relationship is y divided by x, or 4 divided by 3. Y is equal to 4/3 x. So however many number of hours you work, you get paid 4/3 that number of hours in dollars. So y equals 4/3 x. So 3 hours, you get paid $4. Graph 6, you work 2 hours, x equals 2 right here, and you get paid $3 for working that 2 hours. So that relationship is y is 3, x is 2. So for every number of hours you work, you get paid 3/2 that amount in dollars. So y equals 3/2 x. So x is 2, y is equal to 3. $3 for working 2 hours. And the last one, graph 5, is you work 2 hours, x equals 2, and you get paid $4. So in this case, you get paid twice as many. 4 divided by 2 is 2. You get paid twice as many dollars per hour's worked. So the number of hours you worked, you get paid twice that amount in dollars. So y equals 4/2 x. So y is 4, x is 2, y is 4. That's the amount of money you get paid for working 2 hours. So $4 for working 2 hours. Now if we look at that again, so again, here's y equals x. And notice as you go up, these graphs show you who's getting paid more money. The slant of the graph is a higher constant proportionality. That means a higher amount per 1 hour. For working 1 hour, you're getting paid more money as you go from graph 4 up to graph 5 this way. So I want to show that in a drawing. So that's what I'm going to do now. So let's compare what happens at 1 hour. So this was 1/4, y equals $1 for every 4 hours of work. So that's 1/4 of a dollar per 1 hour. So this is 1/4 of a dollar. 1/4 of this whole thing, this whole rectangle represents a dollar. You're getting paid 1/4 of that. So this is 1/4 of a dollar per 1 hour. Graph number 2. This is for every 3 hours of work, you get paid $2. Well, for 1 hour, that's getting paid 2/3 of a dollar per hour. So this is 2/3 over 1. That's the same as $2 right here for 3 hours of work. So $2 for 3 hours of work is the same as 2/3 of a dollar per hour. So this is the per hour right here, and this is the whole number, $2 per 3 hours. So here, if this represents $1, you're getting paid 2/3 of that dollar for 1 hour of work. I'm sorry, if this represents 1 hour, you're getting paid 2/3 of a dollar for that 1 hour. If you work 5 hours, you get paid $4. So that's like getting paid 4/5 of a dollar per hour. So 1 hour, you get paid 4/5 of a dollar. So if this rectangle represents 1 hour, you're getting paid 4/5 of a dollar for that 1 hour. So this is 4/5 per 1, which is the same as $4 per 5 hours. So what I'm trying to do, or what the authors are trying to do, is give you an idea of how the whole numbers, 4 out of 5, $4, for example, per 5 hours of work, is the same as 4/5 of 1 hour. 4/5 dollars per 1 hour. This is 4/3 dollars per 1 hour, or $4 for 3 hours of work. That's the same as, if this is 1 unit, that's the same as 4/3 dollars, or 1 1/3 dollars for 1 hour of work. So it's 4/3 right here, 4/3 per 1 hour of work. So now we're going up, getting paid more money each time we go up, or each time the slant gets steeper. 4/3 of a dollar per hour, $4 for working 3 hours. This is $3 for working 2 hours. So y is 3, and X is 2. So right here, $3 for working 2 hours is the same as getting paid $3.50. I'm sorry, $3.50 per 1 hour. So this is 3/2, so this is $1.50 per 1 hour. So $3.50 is the same as $3 for working 2 hours. $3 working 2 hours. And the last one, you get paid $4 for working 2 hours. This is $4 for working 2 hours, which is the same as $4.50, same as $2, by the way. $4.50 per hour, or $2 per hour, is the same as $4 for working every 2 hours. So again, the relationship of the whole numbers, 4 per 2, compared to the relationship of at 1 hour, or a unit x equals 1, is the constant of proportionality. It's what's the value at 1 hour. That's the constant of proportionality. In this case, it's 4/2. So let's look at this again. This is how it's given to you in your workbook. So here's graph number 1. Graph number 1 matches equation B. So it's 4 out of 5. So this is 4. If we're going to talk about dollars again, this would be $4 out of 5 hours of work. So 4 out of 5 is the same as 4/5 per 1. It's 4/5 per 1. So y is equal to 4/5 per 1. But then if you go to 5 hours, 4/5 times 5 is equal to that 4 right here. So 4/5 times 5 is equal to 1. 4/5 times 1 is 4/5. So it's 4/5 per 1, which is the same as 4 per 5. This is graph 2. That matches equation D. This is 2 out of every 3. So 2 out of every 3, or $2 per 3 hours of work, is the same as 2/3 of a dollar per 1 hour of work. So 2 out of every 3 is the same as 2/3 per 1 is equal to 2/3. So 2/3 per 1 is the same as 2 out of every 3. And the point is that they lie on the same line. This is graph 3 matches equation E. So y equals 4/3 x. So $4 for every 3 hours of work, for example, or 4 per 3, is the same as 4/3 dollars for 1 hour. So that's the constant of proportionality. Once I know that, then I multiply each hour by 4/3. So once I get to 3 hours, 3 times 4/3, x is 3, times 4/3, y is going to equal 4. 3 times 4/3 is 4. So that's 4 per 3. It's the same as 4/3 for every 1 hour, or per 1. This is problem number 4. It matches equation C. So this is the least amount of money, or the smallest relationship of y to x. So y is equal to 1/4 whatever the value of x is. So y right here is 1/4 of whatever the value of x is. So y equals 1/4 x. So if we talk about dollars per hour, once again, you work 4 hours, you only get paid $1. That's the same as 1/4 of a dollar for 1 hour. So 1 out of every 4, 1 out of every 4 is the same as 1/4 out of every 1. So 1 out of every 4 is the same as 1/4 per 1. 1/4 per 1, same as 1 out of every 4. And that equation tells you that whatever number of hours you work, you get paid 1/4 that number of hours in dollars. Graph 5 matches equation A. This is getting paid the most. getting paid the most. So $4 for every 2 hours of work is the same as 4 halves dollars for 1 hour of work. Well, 4 halves is the same as $2. So 4 for every 2 is the same as 4 halves for just 1 hour. And the last one, graph 6 matches equation F. So that is 3 halves. So 3 for every 2. So let's say it's $3 for every 2 hours of work. That's the same as 3 halves dollars for every 1 hour of work. So y equals 3 halves x. So this tells you, the 3 halves, the constant proportionality, tells you what to multiply the number of hours by. So that relationship is 3 halves times, if I work for 2 hours, 3 halves times 2, I'm going to get paid $3. For 3 for every 2 is the same as 3 halves for every 1 hour. So the constant proportionality is 3 halves. This is problem 2, and in this problem, you are comparing the cost of coffee at a coffee shop, so how many dollars for how much volume compared to the calories in each cup of coffee, the different sizes of coffee that you purchase. So which graph goes with calories and which graph goes with dollars or with cost? And probably the easiest way to look at this is to look at this axis right here and notice that they're in the hundreds, 100, 150, 200, 250, and so on. So for a 10-ounce cup of coffee, you're not going to pay $150. That doesn't make any sense. But over here for a 10-ounce cup of coffee, so that's a single cup of coffee, costs $3.75. That makes more sense. So the graph on the left is going to be dollars per ounces of coffee, and the graph on the right are going to be number of calories per ounces of coffee. So this is $3.75 for 10 ounces and 150 calories per 10 ounces. Now the coffee, as the volume increases, the price actually goes down. You can do that with the price. You can change the relationship of the price per volume, because if you buy more coffee, you might give people a better deal. So it might cost you less amount of money per ounce if you buy a larger cup of coffee. You can't change the relationship for calories. That is fixed. There's nothing that you can do about that. You have so many calories per cup of coffee. So which graph goes with which? Once again, this is dollars, and they use this word versus, dollars versus volume. And people often talk about graphs in that way. They talk about whatever the y value is versus what the x value is. So this is dollars versus volume, and this is calories versus volume. And calories is essentially proportional. It's almost a straight line. It's not quite a straight line, but it's almost a straight line. It goes to 0, 0, the origin. You can draw dollars per volume, or the cost, through 0, 0 also, but this is not a straight line. So as you purchase larger amounts of coffee, the cost actually is going down. So they're giving you a better deal. So the dollars per ounce is getting less as you buy a larger volume of coffee. This should be a straight line. It's not quite a straight line, so it gives the impression that what they're doing is some kind of experiment. They're measuring the number of calories per ounce at 12 ounces, 16 ounces, 24 ounces, and they're figuring out how many calories there are for each of those ounces, and they're putting it on the graph. And it's almost a straight line, not quite a straight line, but the constant proportionality you can get from this point right here. So 150 calories per 10 ounces is 15 calories per ounce. So that is the constant of proportionality. And it tells you if you buy 1 ounce of coffee, how many calories are in that, or if you have 1 ounce of coffee, how many calories are in that 1 ounce. Once you know that, you can use that constant proportionality to calculate the number of calories for any number of ounces. So if I go out here to 10 ounces, that's where we start. Actually, skip over to 12 ounces. So if I have 12 ounces of coffee, how many calories of that? Well, that's, how many calories is that? That's the number of calories per ounce times 12 ounces. So 12 times 15 equals 180 calories. So that should be 180 right there. It looks like it. I'm sorry, 180 right here. It looks like it's a little bit above that. A straight line would be right here. So this is probably, or this is 180 calories, and what they measured was a little bit more than that, but it's pretty close. That's okay. 16 ounces. Well, if it's 15, it's going to cost me 15, or it's going to be 15 calories per 1 ounce. If I have 16 ounces of coffee, how many calories is that? Well, that's 16 ounces times 15 calories per 1 ounce. That equals 240 calories. So if I go out here to 16 ounces and I go up to this point right here, it should be 240 calories. It's a little bit more. It's really closer to 250 on the graph. It should be 240. And out here at 24 ounces, if I have 24 ounces of coffee, how many calories of that is that? Well, it's 24 ounces times that 15 calories per 1 ounce. So 15 times 24 equals 360, and that's what the value is for out here at 24 ounces. It is 360 calories right there. So calories is proportional. You can't change that all unless you change what you're putting into the coffee, but this is not doing that. This is just changing the volume of the same thing. So you cannot change that relationship. That relationship is fixed. Whereas you can change the relationship of dollars per ounce. You're the owner, you can charge what you want, and you can give people a better deal if they buy more coffee. In this last problem, problem number 3, we're looking at Lynn and Andre riding their bikes home from school. Both of them are riding at a steady pace, and the question is to create a graph of their trip and ask who's riding faster, who's riding slower, and what's the constant of proportionality. That's the value when x equals 1, the value of y when x equals 1. So just a minor point to start off with. They talk about that both of them are riding at a steady pace. Now, pace is actually time per distance. So time would be on the y-axis, distance would be on the x-axis. And I actually set this graph up as speed. Speed is distance per time. Now, this is a minor point. Actually, the authors don't even, they drew the same graph, and they don't raise this issue, but they're riding at a steady pace. And if I were to write this, I'd say that Lynn and Andre biked home from school at a steady rate. Rate is speed. It's distance per time. Pace is time per distance. So we talk about, for pace, we talk about an 8-minute mile. So 8 minutes per 1 mile, or a 10-minute mile, or a 7-minute mile. For speed, we talk about miles, distance per hour, or kilometers per minute. So I graphed this as speed. Lynn biked 1.5 kilometers and it took her 5 minutes. Andre biked 2 kilometers and it took him 8 minutes. So we can place those 2 points. Lynn is 5 minutes, 1.5 kilometers. So we know this is Lynn because that's what the story tells us. And Andre is 8 minutes and he biked 2 kilometers in those 8 minutes. So this is Andre and this is Lynn. Now this slant, Lynn is slanted, is a slightly steeper, a little bit more of a slant than Andre, so she is actually biking faster. We're going to find out that the more the slant is, if you graph distance per time, that means the faster that she's moving. So Andre is at 8 minutes and he traveled 2 kilometers. So that's 2 kilometers per 8 minutes. So that's equal to 1/4. So 1 kilometer every 4 minutes, which makes sense. 1 kilometer every 4 minutes, or 25 hundredths of a kilometer in 1 minute. So 1/4 of a kilometer in 1 minute. So this value right here is 1/4. This is 1/2. Half of 1/2 is 1/4. So when x is 1, when you're at 1 minute, how far have you traveled? You've traveled 1/4 of a kilometer. So when x is 1, y is 1/4. This is the constant of proportionality, 25 hundredths of a kilometer per minute. For Lynn traveled 1.5 kilometers in 5 minutes. She's out here at 5 minutes, 1.5 kilometers. So that constant of proportionality is 3/10. So 1.5 divided by 5. You can rewrite the 1.5 as 5 times 3/10. These 5s cancel out. You're left with 3/10. So Lynn is traveling at 3/10 of a kilometer. This is this point right here. That's 3/10 of a kilometer per minute, or 1.5 kilometers per 5 minutes. So Lynn is traveling faster. Her constant of proportionality is slightly greater, and it's not that much greater. It's just slightly greater than Andre's. And that constant of proportionality tells you how long it takes her to travel 1 minute. And then for however many minutes she travels, you just multiply that by 3/10. That will give you her distance traveled. So if she travels 5 minutes, her distance traveled is 1.5 kilometers, because 5 times that 3/10 kilometers per minute equals this 1.5 kilometers. So 5 minutes, 1.5 kilometers, so that's 1.5 kilometers per 5 minutes. 8 minutes, 2 kilometers, so that's 2 kilometers per 8 minutes. And those simplify to 25 hundredths kilometers in 1 minute, or 3/10 of a kilometer in, right here, 3/10 of a kilometer in 1 minute. So Lynn is traveling slightly faster. Now we could talk about how much faster in terms of how many times faster, or just how much faster in terms of just additional time per minute. So Lynn is riding faster than Andre. She's riding at 3/10 of a kilometer in every 1 minute. Andre is riding at 25 hundredths of a kilometer in every one minute. So in every minute, Lynn travels, for each minute, Lynn travels 5 hundredths of a kilometer farther. So this is 0.05 plus 25 is going to give you this 30 right here, 3/10. So 5 hundredths of a kilometer farther for every minute traveled. So 3/10 of a kilometer per minute and 25 hundredths kilometers per minute. Lynn is riding faster.